I'm Nitin, and this is Nibir. Today's topic, today's demonstration is on the integration of structural health monitoring through simulation. It's part of the Indus consortium, the members being University of Saarland and IMA Dresden from Germany, and Indian Institute of Science and Tech Mahindra from Bangalore. Let me start out by asking why do we require simulation? It is to maximize the probability of detection under varying conditions. Typical NDT requires a huge number of iterations generating huge data set, while simulation requires one model and same number of data sets, thereby reducing the number of iterations required. We start out with the SHM verification validation process by loading databases of the fatigue loads, then loading the geometry of the component, performing static analysis, performing fatigue analysis, which drives how the sensors have to be mounted with respect to a damage, thereby driving the SHM simulation, and then we'll show you the experimental validation. These are the softwares which we use to validate our software. So we have taken a sample which is subjected to load, and this is the damage tolerance criteria. Here we present a stress and probability of damage accumulation for a damaged and undamaged sample. You can see the stress interacting with the complex geometries present in the panel. There is also a residual strength which is being monitored. Residual strength varies over damage size. You can see how the stress varies over different damage sizes here. We also generated something called as a detection curve, which is basically a correlation curve over varying damage size. So this is generated through simulation, and then this can be superimposed with data from real-time data, which then gives us the damage size. Let us give you a demo of the demonstration.
Yeah. So this is a tool that we have been developing for our simulation purpose. So what you see here, we have loaded the finite element model of a stiffened metal panel, the schematic block diagram of which has been shown in our PPT. Here you see there is a blue region, which is the region I have selected for running our guided wave simulation. Just let me switch to the front view and I will zoom in the selection region. So here you can see these are the rivet holes, and here is a crack present in the structure. Now I want someone from the audience to prescribe me the location of the actuator and sensor. What would you like to place me?
5 seconds.
Somewhere here, please. Okay. Yeah, I will put my actuator here, and let me place the sensor here. And let me run the simulation. So while it is running, let me tell you the feature of the tool that we have been developing. This is basically a simulation tool, but not only simulation. We are able to collect real-time data using the same tool and fuse the real-time data along on the simulation. This tool is able to handle any sort of complex geometry through finite element BDF files, which is a standard BDF files. And then we are able to fuse in fatigue analysis and static analysis results so that you can superimpose the stress contour and POD contour on top of the same mesh. Okay, now the simulation is complete, and here you see the expected sensor signal, where this particular one is the reflected packet from the crack.
Okay. Here is a demonstration of the guided wave propagating on the same material, the same sample, recorded using a laser vibrometer. As you can see, the wave packet is propagating, and there is a crack that is present. There is a packet that gets reflected off the crack. So intuitively, you could place a couple of sensors near the actuator position and along the path of the reflected packet. Based on this assumption, we took 4 sensors we have placed in this configuration, and I'll show you a video of how we perform the test. We start out with panel fabrication. We created sensor interconnects. We then bonded sensors to record the guided waves. We also bonded strain gauges to measure the strain around the crack tips. We now start with the SHM test process. So the tool that we developed can do both the simulation as well as real-time data recording. So as you can see, we just initiated the loading, and we are also starting with the data acquisition. The loading is happening right now. So as the loading happens, we collect data real time. We then cut through the stringer to create a notch. And now we type the real-time fusion of data with the simulation data. So now this is happening real time. We cut a 35 notch and then the crack has been detected. This is a graph, so we are superimposing the data that we collected with the simulated graph. There is a crack that was initiated at 50,000 cycles. And as you can see, this was progressively done, and over different crack sizes we monitored. So the data was fused against the different curves that we had generated. So as you can see, there are two different kinds of curves that you can generate using the same software based on your requirement. Some curves can behave well, some does not. So here we present you a simulated tool where you can fuse real-time data and determine the crack size immediately. Thank you.